Hello, welcome back. In this video, what we're going to do is talk about powers of numbers in congruences. So what I mean is the following. Recall that in a previous video, we learned about the fast powering algorithm. And what this means is that to compute something like 3 to the 123rd power, one does not have to complete the entire expansion. If you just want to know, for example, what is it modulo 100, because I wanted to know what are the first two digits, what we did is just use the power of congruences to actually compute higher and higher powers, and then use the binary expansion of 1 to 3 to compute that modulo 100. And in doing so this was one way of doing it, but we came up with another way, which was that as I took powers, I found that 3 to the 20 is 1 modulo 100, and that helped me a lot, because knowing that 3 to the 20 is 1 modulo 100 means that I can do long division of 123 by 20, and then use that, because 3 to the 20 is 1, to simplify the calculation a lot, and that led me to 27. So the question here is, how did I find this in the first place? How did I know that 3 to the 20 would give me something like that? And in general, how do I find powers of numbers that are going to give me the congruence of 1, so that I can use that in my favor? So here are some examples. What happens with powers of numbers modulo 5 and modulo 7? So I've made a table here for the units modulo 5 and for the units modulo 7. If you start with 0, 0 squared is 0 times 0 is 0, and so on. So there would be, if I put the 0, there would be an entire row of zeros here, and I don't want that. But what happens with the other ones? The powers of 1 are all 1s. The powers of 2 are 2, 4, 3, 1. How am I calculating that, by the way? I'm calculating that by saying, like, well, 2 squared is 4. 2 times 4 is 8. Reduce modulo 5, and I get 3. Okay, so 2 times 4 is 8. Reduce that modulo 5, I get 3. 3 times 2 is 6, and 6 is 1 modulo 2. And you see that once this tells me that 2 to the 4 is 1 modulo 5. So that is one of those instances I was talking about before of a power of a number that gives me 1. And that can be used in general to find high powers of 2 modulo 5. That would be very useful in general. And also useful is because once that happens, the next one will be 2, and then 4, 3, 1, and then 2, 4, 3, 1. So this cycle will repeat over and over again ever after. What happens with 3? 3 squared is 9, which is 4 modulo 5. 4 times 3 is 12, and 12 is 2 modulo 5, and 3 times 2 is 6, which is 1. And then you see that again, we get that cycle will repeat, 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 and also we get the information that 3 to the 4 is actually 1 modulo 5, and that's the first time it happens. For 4, you see 4 is minus 1 modulo 5. So minus 1 times minus 1 will give me 1. So actually, the first time that 4 to a power is 1 modulo 5, that is for 4 squared. So here, what I actually get, my information that I get is that 4 squared is 1 modulo 5. So it happens before for 4 than it happens for 2 or for 3. What happens for modulo 7? Modulo 7, we get, for example, 2, 4, 1. So some elements have cycles of order 3. Some elements have cycles of order 2. And some other ones have cycles of order 6. You see, of length 6. But what is quite surprising is that they all agree here, all somehow match here. And the same way, they all match here. You see that every number modulo 5, every non-zero number to the every non-zero number, every unit to the 4th power gives me 1, every unit modulo 7 to the 6th power gives me 1. So I can write that in here. So this tells me that actually a to the 6 is 1 modulo 7, as long as a is not 0 modulo 7. That always happens, which is really interesting. And by the way, when that happens, you see that I get a column where all the numbers are in order. You see here, they are all scrambled numbers, but in the 7th one, they all become, again, in order. The same thing happens for the 5th power here. They are all in order. And in fact, if you add the row of zeros, there would be a 0 here. So they would really be all in order. So this tells me also that a to the 7 is congruent to a modulo 7, or all a, and a to the 5 are congruent to a modulo 5 for all integers. So those are very interesting patterns. And is that true? Is that true in general, that we have that property? Let's look at powers modulo 11. Does this happen for all numbers? Well, let's see. What would have been the pattern, by the way, that we're seeing here? They are at different powers. So what power is that? What power is this? And what power is that? And what power is this? Clearly, this 7 and that 7 seem to be related, and that 5 and that 5 seem to be related. So the conjecture would be that if you have an n, that we have that a to the n is congruent to a modulo n. This is not true actually for n when n is not prime, but when n is prime, it seems to hold. You see for 11, if you go to the 10th power, they all match. Let me box it like this, that the 10th power of every integer seems to be congruent to 1 modulo 11. For every unit class, if you put in, for every non-unit class, and every number to the 11th power is congruent to itself. There will be here, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The next column would be that column. So this tells me that a to the 10 is congruent to 1 modulo 11 for all integers a that are not 0 modulo 11. So not divisible by 11, then the 10th power will be 1. And that precisely is the statement of Fermat's little theorem. So let's put it here. Fermat's little theorem, little as opposed to his last theorem, which is very famous. Okay, so what does Fermat's little theorem says? Here is the statement. It says that for a prime number, it's not true for non-prime numbers. For non-prime numbers, you have to do something that's called Euler's theorem. But for, let's switch to not calligraphic pen. Let P be a prime, and let A be an integer. Then, first, A to the P is congruent to A modulo P for every integer A. And also, if P does not divide A, then A to the P minus 1 is congruent to 1 modulo P. So that is what Fermat's little theorem says. Let me show you, let's prove, show that Fermat's little theorem actually holds for 3. I'm going to show that 3 to the 10 is 1 modulo 11, which was part of the table that I just showed you. But I want to show it using what actually generalizes to be a full proof of Fermat's little theorem. So I'm going to do it in a way that if you replace 3 by a and 11 by a prime, actually this is a proof of Fermat's little theorem. So let's start with z mod 11z cross. So the units are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Those are the units modulo 11. And what I'm going to do is I'm going to multiply by 3 and reduce every one of those numbers. And when I do so, what numbers do I get? I get 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12, but 12 modulo 11 is 1. 3 times 5 is 15, and 15 is, what is 15 is 4, and so on. Let me just copy it down so I don't make mistakes. 7, 10, 2, 5, and 8. And what you should notice is that actually I got everything back. You see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And I got all of them in some more or less random order, but I got all of them back. Okay, so then what I can do is the following. Then multiply all of them together, all of the numbers that I just got. So 3 times 6 times 9 times 1 times 4 times 7 times 10 times 2 times 5 times 8. How much is that? Well, that is, I just figure out that that was 3 times 1, 3 times 2, up to 3 times 10. And now multiplication in modulo 11 is associative. So I can actually take all those 3 and distributive. I can take all those 3's and multiply them together first. You see there are 1, 2, 10 3's. So what I get is 3 to the 10 times, and then the rest of the numbers were 1 times 2 times 3 up to 10. Okay. So this is 3 to the 10 times 10 factorial, if you want, 1 times 2 times 3, and so on. And on the other hand, multiplying all of the numbers together in a different order, again, I can reorganize these as, well, these are just the same as 1 times 2 times 3, up to 10. So it is 10 factorial also. So what I just got is that 10 factorial, whatever that number is 3 to the 10 times 10 factorial modulo 11. Now, 10 factorial is a unit. Let's call this B. Is a unit modulo 11. I don't know what it is. I haven't multiplied it yet. It's in fact equal to -1 because of some other theorem, Wilson's theorem, but we don't know that. So B is a unit, meaning that B has to have a multiplicative inverse because B is not divisible by 11. B is a number that is relatively prime to 11, and those are units. So there is an inverse modulo 11. So I can multiply both sides by the inverse of 10 factorial. Oops. This is 3 to the 10 times B inverse times 10 factorial modulo 11. But then because I multiply by the inverse, these two cancel out and these two cancel out. And what I get is that 1 is congruent to 3 to the 10 modulo 11. So I get what I wanted, that 3 to the 10 is 1 modulo 11. Okay, so this technique, as I said, can be generalized to prove Fermat's little theorem in general. What you do is you have A to the P-1 and P. You write all the numbers from 1 up to P-1, multiply them by A, and then write that that is going to be the P-1 factorial. And also it is going to be a to the p minus 1 times p minus 1 factorial, but p minus 1 factorial is a unit, so it can be crossed out from both ends and get that 1 is a to the p minus 1. Okay, so that's a proof of Fermat's little theorem right there. Great. Why is this useful? Fermat's little theorem, because it helps, again, with that fast powering algorithm, it helps a lot. So for example, let's compute 27 to the power of 35,678 modulo 11. Okay, so first of all, 27 to the 35678, I can simplify the base of that exponent. Okay, so I can simplify, this is the base, this is the exponent. This I can reduce modulo 11. Modulo 11, that is 5 to the 35,678. Okay, now what can I do? Now I know from Fermat's little theorem, 5 is a unit, modulo 10. So I know from Fermat's little theorem tells me that 5 to the 10 is congruent to 1 modulo 11. So what I'm going to do is actually write this exponent as 3567 times 10 plus 8. And then by the laws of exponents, this is 5 to the 10 to the 3567 exponent times 5 to the 8. But now is where I also use Fermat's little theorem here to say that 5 to the 10 is actually 1 to a very large power. That's just 1. So that is 1 times 5 to the 8. So this is just going to be 5 to the 8, whatever that is. And 5 to the 8, I can compute by hand. 5, then 5 squared is 25, but 25 is 22 plus 3, so this is 3. Then 5 cubed will be 5 squared times 5, so it will be 3 times 5, it will be 15, which is what? 15 is 4. Actually, I didn't need to do 5 to the 3, I needed to do 5 to the 4, which will be 5 squared a square, so it's 3 squared, which is 9. And then 5 to the 8 is 5 to the 4 squared, will be 9 squared, which will be 81, which is 77 plus 4. So it is 4 modulo 11. So 5 to the 8 is 4, so this is just 4 modulo 11, final answer. So this is just 4 modulo 11. Okay. Is Fermat's little theorem true for non-prime moduli? Suppose I want to work modulo 15. Is it true? Is it true that unit to the 14th power is congruent to 1 modulo 15? Let's try 2. For example, 2 is relatively prime to 15. How much is 2 to the 14th power modulo 15? Well, I can start computing. 2 squared is 4. 2 to the 4 is 16, which is 1. Okay, that's very helpful because then 2 to the 14 is 2 to the 14, do long division by 4. That's 4 times 3, 12 plus 2. So this is 2 to the 4 to the 3 times 2 squared. So that is 1 to the 3 times 2 squared. So this is 1 times 2 squared. So this is 1 times 4. So this is just 4. But that's not 1. So Fermat's little theorem does not hold for non-prime moduli. What is true, though, is Euler's theorem, which is something else. Okay. This, by the way, also gives me a way of checking primality. So, for example, is the number 154852007 prime? If so, by Fermat's little theorem, we would have that 2 to the p minus 1 has to be 1 modulo p. But it turns out that you can compute that 2 to the 154852006 is, you can do fast powering algorithm and check that it's congruent to 4136685 modulo this number 154852007, which is not 1. So this number p is actually not prime. So that is not a prime. Great. Very good. Okay, so I'm going to stop there. And in the next video, I'm going to talk about primitive roots.